All right, so we were in the middle of section 1.3 last time. We talked about these words analytically and algebraically, and that they're interchangeable. And so when you see them in direction sets, you'll be able to change them out for one another. And we had encountered the idea that sometimes when we plug a value in, we get a 0 in the denominator. And if in fact we also get a 0 in the numerator, then there will be some way that we can manipulate the expressions. And we saw two examples of that where we used factoring, right? We were able to factor something, cancel it out, then we can evaluate it by plugging in the value that the x is approaching. And once we do that, we have our limit. This one right here is where we were. And in fact, the 0, x approaching 0, makes the denominator 0, but it makes the numerator a 0 as well, right? If I have the numerator, if I have x as 0 in my numerator, I get square root of 2 minus square root of 2, which is 0. So there is going to be a way to simplify this. This just doesn't look like factoring. And I mentioned briefly last time that it's going to involve conjugates. So the conjugate is the same value that we have with the opposite sign. So on the top we have the square root of 2 plus x, and then plus the square root of 2. And anytime we multiply a fraction's numerator to keep equal fractions, we multiply the denominator by the same value. Like that. So why do we like conjugates? Well, let's take a look at the example that I gave above where I had the a plus b and the a minus b. When we multiply conjugates together, we actually get the middle terms eliminating one another. So I would have a squared, I would have plus ab, and then minus ab, and then minus b squared. And it always happens that the middle two terms are the same with opposite signs and they cancel. You also have seen this before, and it was called the difference of squares when it's be given in the final form right here, right? The difference of two things squared. And it has this unique factoring that's actually conjugates. So the numerator, when I'm multiplying it by its conjugate, will have this feature. So I will end up multiplying the first two terms by each other, right? So I have this piece and this piece being multiplied, which is going to give me what? What happens when I multiply square root of 2 plus x times square root of 2 plus x? I get the square roots to eliminate, and I'm just left with 2 plus x. And the same thing will happen with the other two, right? So on the other two, when I multiply the square root of 2 and the square root of 2, I get 2, and it's negative, yeah, because of the negative in front of one of them. All of this is the limit as x goes to 0, and the denominator stays the same. Like, as in, I'm not going to distribute it through, is what I mean to say. So I'm going to leave it as the x, and then times the square root of 2 plus x, and plus the square root of 2. Okay, is that all right? What do you notice happens in the top? Yep, the 2's cancel. And so now I only have x on top. But not only do I have x on top, I have a factor of x on the bottom, right? So those will also divide out. So this divides with this one. That happens only because it's a multiple on the bottom, right, a factor of it. So now I have the limit as x goes to 0 of 1 over square root of 2 plus x plus the square root of 2. Can I plug 0 in for x now? It can. It won't make the denominator 0, will it? And it's because the signs are different than they were before. So now I will have 1 over square root of 2 plus the square root of 2, otherwise known as what? 2 square root of 2. We aren't going to leave a radical in the denominator when it's just got a constant underneath it, right? We've learned this phrase called rationalizing the denominator, probably in an algebra course or a pre-calc course. So when I have that square root of 2 in the denominator, I'm going to multiply the top and the bottom by square root of 2. So the top will be square root of 2. And then on the bottom, when I multiply these two square root of 2's, I get 2 times the other 2 that's already there. So I'll end up with 4. And I can't reduce the 2 and the 4, if you'll remember, because the 2 is underneath the radical, and the 4 is not underneath the radical. So square root of 2 over 4. This is a really good example of one where if you were trying to do a numerical method, like with the tables, it would not tell you square root of 2 over 4 in your calculator, right? So if you wanted to check this with another method, you'd have to, at the very best, just check the decimal representations that they're giving you something that's exceedingly close to one another. Because it can't get square root of 2 over 4 out of the calculator when I use a table. Does that make sense? And also using it from the perspective of a graph would be not possible either, yeah? It would be an estimation at best for what it looks like it's approaching. All right, any questions on that one? You'll have a couple that you're going to practice that are going to have radicals in them. All right, so we're going to shift gears a little bit to look at some trig. If it's been a while since you've done some trig, you want some refreshers about different properties or ideas, there are some within your textbook. So in the front flaps and the back flaps of the actual book, there's some. If you look at the ebook online, you'll be able to find them as well. I actually also posted inside of our Canvas classroom a Trig Identities sheet. That will be helpful as we continue on our way. So if you don't have that printed and you think that that might be helpful, please print that out. The list of trig identities, limits of them. So let C be a real number on the domain of the given trig function. So some of our trig functions domain is all real numbers, like sine and cosine. Some of it have asymptotes that come periodically, like tangent, cotangent, secant, and cosecant. But as long as we have a value that's actually in the domain, we can do just like we did with polynomials and rational functions and radicals, all the rest, composites. We can just evaluate the function sine at the value of c, cosine at the value of c, and so on, as long as the c is in the domain. So once again, it's like what we would expect to have happen is happening. It's lovely. It's very nice when those things occur. We do need a couple of special trig identity limits that are not necessarily obvious from looking at them. We could verify them graphically. We could verify them numerically. But these are our two special trig limits. If you have sine of x over x and x is approaching 0, the sine of 0 is equal to what? Remember? Is it 0 or is it 1?
0.
It's 0. Yeah, the sine of 0 is 0. So if I were to just plug in 0 into this function, right, for x, I get sine of 0, which is 0 on top, and I'd have 0 on the bottom. So that 0 over 0 has to change to something, and for this particular one, that limit actually approaches 1. And again, we could verify it with a numerical approach. We could verify it by looking at a graph. But it will approach the value of 1. The other one is quite similar. It's talking about cosine. If the cosine value of 0, if x is approaching 0, what is the cosine of 0? Nope. It's a good guess. 1. Cosine of 0 is equal to 1. So on the top of this thing, I'd end up with 1 minus 1, so the numerator would be 0, and the denominator would be a 0 as well. So again, on this one, that limit, if we looked at it numerically or algebraic or graphically, excuse me, would actually approach the value of 0. So these are values that you can take at face value. We're not asking you to prove them, right? But you're going to use them when you find them necessary in showing other limits. Okay? So we'll do some examples where some of these things are going to show up. Okay, so again, if we can just plug the value in, that's what we do. And here's an example of one where we should be able to do that. I don't have any denominator that's a variable here. I just have 2 in a denominator inside of sine. So if I plug in 2 for x, I would have sine of pi times 2, or you could write 2 pi over 2. So 2 pi over 2 would equal what? Pi. And what is the sine of pi? The sine of pi is equal to 0. So it's either zeros or ones are going to be showing up a lot on some of these values. Let me remind you that if you haven't seen it in a while, the unit circle can be a good tool. You might even want to print it out. You can print out, if you just Google unit circle images, you'll find one and you can print it out and it'll have all the details on them. So if we look at the sine value at pi, so this is 0, this is pi halves, this one is pi, and this one is 3 pi halves. So the dot that I made at pi, sine is the y value. What is the y value at that point? It's 0. If I were asked for the cosine value at that point, it would actually be 1, negative 1. Okay, so you get a lot of 1s and negative 1s. Number 7 doesn't do that, though. Number 7 is not approaching a value that's quite as friendly when we look into it as a unit circle perspective. So we're going to look at cosine of 5 pi over 6. So 5 pi over 6 on the unit circle is over here, and I don't want to belabor the unit circle too much because I know you can go back and print it out. I know you've seen it before. Even if it's been a while, you've seen this before. So just to refresh yourself on the unit circle. Okay, so 5 pi over 6 is the third one of the unit values in the second quadrant, okay? And we want the sine value. So at these intervals where we're here, the first one and the third one, we're at values that are square root of 3 over 2 and 1/2. I mean, that's what they are. Those are the ordered pairs that we're at. So the first one is actually a negative 1/2 and then square root 3 over 2. The second one, the one that was actually that we have, is the opposite. It's negative square root 3 over 2 and then 1/2. Okay, so that should look at least familiar even if you couldn't have like written them down from scratch right now on your own. Does that look familiar? Okay. And then the sine value is the y value. So what's the y value for our ordered pair point that we're looking at here? It's cosine value. Sorry, cosine value is what I'm asking for. Yes. Yeah, negative square root 3 over 2. So it's going to be very helpful for you to print out a unit circle or at least have one pulled up if you're doing your homework with it or whatever until you can refamiliarize yourself with those features. Okay, the next two are a little bit more interesting because they're not just, let's go to the unit circle. So let's take a look at number 8. Number 8 is the limit as x approaches 0 of sine of x over 5x. Now, it's not exactly the first one of these, number 1, but it's very similar. How does it differ from that first property on this screen? There's a 5, and where is it? There's a 5 in the denominator that's showing up, right? So we have to be able to sort of make amends for the 5 in the denominator, but it seems reasonable that we should be able to use that limit feature if we could fix the 5, right? If we could somehow ignore the 5. And we actually can. So one of our properties that we discussed, I can't remember if it was last time or 2 class periods ago, but we talked about constant multipliers. And constant multipliers of limits have the ability to be pulled out in front of the limit. They don't affect the limit. I actually think it's in this lesson. Let me see if I can show it to you. It's that one. Scalar multiple. So when I have b times my function value, I'm able to pull the b out in front and then use whatever the limit is that I know that the limit will be. So this is actually the other piece that we're going to be using on number 8. So the first thing we need to do is we actually need to pull that 1/5, because it's 5 in the bottom, so 1/5 out in front. And then I have the limit as x approaches 0 of sine of x over x. Is that okay? Constant multiplier rule says I'm able to do that. Why is that good? Well, because I have a limit value for this. What is the value of the limit as x approaches 0 of sine of x over x? Was 1. So this is 1/5 times 1, or 1/5. No unit circles, right? Not on that one. Any questions on that? Okay, we're going to do something a little bit different then on the next one. This one has cosine and it has tangent in it. So this is where using trig properties that are ones from the past, the ones I've posted inside there as a reminder too, are going to be helpful. So sine and cosine and tangent all have sort of this interesting relationship, right? And the relationship that's usable here, although they will change from time to time on which one's usable where, of course, is the fact that tangent is equal to sine over cosine. Agreed? Okay, so if we have the ability to manipulate, that's a good place to start. We may choose the wrong manipulation. It'll lead us nowhere. We know then we go back and we choose another manipulation. This one works really well. So what happens to the cosines on this? Yeah, they cancel. So we're left with just the sine of x that's on top. So I have the limit as x approaches 0, and it's really just the sine of x over x, but that's 1. That's one of our properties that we actually get to use for free. So manipulating trig functions using trig identities is another option when we're working with trig, kind of like factoring is a good option when we're working with polynomials. Any questions on that? All right.